Alright, moving on to the exposure time calculator, or the ETC. So the ETC is the tool that you want to use to design your observations by simulating basically your astrophysical scene with a given instrument on James Webb. So the ETC will do a real-time simulation to generate your observations. It's not based on pre-calculated performances of the instrument on James Webb. So actually the name is a bit confusing because the ETC will calculate the estimated synchronous ratio of your observation for a given exposure time. The ETC has not the ability to do the reverse calculation, so providing the SNR, it won't return the exposure time you need to reach that level of sensitivity. So the ETC is based on the 3D approach, so both the spatial and the spectral dimension, so it can be used to simulate the imaging and the spectroscopic capabilities on James Webb. With DTC, you will be able to create very complex astrophysical scenes. So these scenes are designed as a small postage stamps of the sky with a few arcseconds in diameter. So the small dimension is only here to save some computing time, otherwise it would be too heavy. So the scenes can be very complex, so you can imagine having multiple sources with point sources, extended, and sources with a multi-component emission. So once your scene is designed, it will be convolved with the monochromatic Webb PSF to mimic as best as possible the expected performances of the observatory. So the ETC handles correlated noise, but also the background emission with several components. So the background on James Webb is affected by the thermal emission of the telescope itself, the stray light, the interstellar medium, but also this zodiacal light. So all this background emission is time dependent, and this dependency is handled quite well by the ETC. So if you want to learn more to play with the background emission, there is a standalone tool on Python that is available on GitHub if you want to play with. So once again, if you want to learn more about the ETC, go to JDocs. There's a lot of information. There are also some demos that are available on JDocs that you want to look at. So the ETC exists in two versions. So there is a web interface that I will use in the demo in a moment. So it handles more the features that you want to use for your simulation. And we encourage you to create a Space Telescope account to be used with the ETC in order to be able to save and to share your works with your collaborator. So the ETC also exists in a Python engine. So this engine basically have a more advanced option, and it can be used with a script. Say if you want to do very intense perimeter space exploration, or if you want to simulate your observation with many targets, that is the way to go. But here we will use the web interface. So let's go directly to the demo. So I will open Safari and search for the ETC on James Webb. Alright. So this is the welcome page of the ETC. So this is where you will be able to create your account on the Space Telescope website. And you also have the two options actually to log in to use the ETC. There is a very basic option to work anonymously. So with this feature, you won't be able to save, note, or share your works. So this is for a single visit purpose, basically. So we encourage you to use the login option, so to use your MyST account. So this is what I will do so far. And now I'm logged in. So this is now the home page of the ETC. The first thing I want to show you is there is the help button here, and I will open up the button. So you have several options with several features. So there are known issues because the ETC is actually the development of the ETC is ongoing. So if you're facing some bugs, it's very likely that this bug is already known. So go to visit this page. There is also a help desk which will send you to the official STACI help desk, not us here at the University of Montreal. Alright, so the ETC is organized in workbooks. So basically a workbook is what's used for a given simulation or given proposal. Every row in this table is associated with the workbook. So for the newcomers, we encourage to use, not to start from scratch actually, but there are many pre-existing templates for the different modes, but also the target acquisition that you want to use to start. But here we will create a new workbook for the purpose of that demo. So I clicked on the workbook and I have now a new row in the table. On the bottom actually of the home page, if I click on my newly created workbook, I have the ability to share this workbook with my collaborators by providing their email address here. And then I can manage the different permission levels. Alright, I'll load the new workbook so it will open a new tab in your browser. So this is how a workbook looks like. So the first item actually is the name of the workbook and the description. And then the workbook is organized in two rows. So the first row is used for the designing your observation, your simulation, basically by providing the different parameters. And the bottom row is dedicated to the outputs. So we will start by clicking on the Scene and Source tab to create my astrophysical scene. So I will make a very simple scene by generating a simple point source, and we'll generate some imaging observation then. So there is a default source, but I don't want this one, so I will delete it. And I will create a new source. So actually the scene and source is designed with three panels. So on the left there is this panel dedicated to the scene. In the middle it's the panel dedicated to the source. So this is where you will create a new source. And the right is the source editor. So basically where you will modify the parameters of a given source. So I will generate a point source. So I will call it HD0. And then you can upload a given spectral effect, a spectral energy distribution to your source. So you have two options here. You can provide your own spectrum. If you do so, click on the tab Upload Spectra. So the spectrum can be provided with an ASCII file, so two columns, the wavelength and the flux. Or you can also upload a FITS file, which has to be compatible with the Python routine generally used to open a FITS file. There's also the option to use some pre-loaded templates, several continuums, several models for stars, other objects, but also some galaxy actually observation from Brundtland 2014. So here we'll use a simple star model, and I will make a fake sun. So G2V. All right. In this panel, you also have the option to add the redshift to the SCD of your source, and also to add some extension using different lows and different intensity for the extension. All right, so now I have the SCD affected to my source. So I want to renormalize the actually observed flux of my source. So three options here. I can normalize at a given wavelength in a given bandpass, and I also have the option to let the flux as it is. So this might be of importance for you if you have already provided your spectra. So here I will create a Fronin magnitude in the Vega Max system in the K-band. That is for my target. Alright. Then you have the option to add emission line. So you will have to enter the line one by one by providing the observed wavelength and the strength of the line. The last tab is the shape of your source, so extended sources using different distribution and different sizes. We here will generate a simple point source. Alright, so my source is now created. I click on Save. And now I have to affect this source to my scene, so I will click here on Add Source. And now we see that both scene and source are highlighted in yellow and green. So the green means a given row is used in another row, and the yellow highlight is when one line is active, basically. So here we see that the source number 2 is used in the scene number 1. So on the bottom row of this page, we have the sketch of the astrophysical scene. So here we see a very small stamp with my point source in the middle. In the central panel, there is the spectrum of our source, which is a stereo spectrum, basically. And on the right panel, it's a the tab that I will show you at the end of the demo. Alright, so then I can apply some offset to my source into my scene. So if you want to apply an offset, you have to do it in the scene environment. Because a given source can be used in multiple scenes, the offset has to be defined in the scene environment. So this is why I've highlighted the scene and the sources. So I will go to the source editor and the offset, and I will apply an offset to my source. I also have the ability to apply some orientation for extended sources, and we see here in the sketch that my source is now on the top left of the scene. Alright, but for the purpose of the demo, I will keep the source at the center of the scene and click on Save. Alright, so now my scene is ready, so we will generate some calculation. So on the left panel, this is the calculation table. So this is a list of all the calculations that you have generated using those templates for each instrument. So we will generate a imaging observation with NIRCam in the short wavelength channel. So by clicking on the template, it will add a new row in the calculation table. So I will select this row. It will open a panel on the right, which is dedicated to the parameters of your observation. So the scene, I will use the scene number 1, and the source in that scene there is a single one, so which is HD0. And see you have some shortcuts for the parameters of your scene, which might be used instead of going to the source and scene tab. Then you have the ability to add some background, so the background will be used in the simulation. So two options to use the backgrounds. If you know the position on the sky and the date of your observation, you can use this option to generate a background which will be simulated at this given date. But if you don't know when you will be able to observe your source, there is the option to use a statistical distribution on the background. So 3 levels, the low, medium, and high, corresponding to the 10%, 50%, and 90% of the emission based on the statistical distribution. So here we assume the source is far from the ecliptic and far from the galactic plane, such that the background emission is low. Moving on to the instrument setup, so this is where you can choose a given filter for your observation. So here I use the F182M filter on NIRCam. There is a plot on the right showing the transmission profile of that given filter. And then the detector setup. So this is one of the most important tab for designing your observation. So this is where you will choose a given readout mode for your observation. So subarrays, we'll use a small subarray for NIRCam because I'm only interested in the point source and its surroundings. And then the readout pattern. So for NIRCam, there are a lot of options here. We will go into the details of the different readout pattern on NIRCam in the next webinar. But here I will use the bright one readout mode because I know the source is quite bright. So if you don't know which one to use, you have 2 options. Either you play with the ETC, so you select one readout pattern, you make your simulation, you look at the given SNR, and you repeat the exercise by using another readout pattern and see whether the SNR has been improved or not. Or you can go to JWST and search for the best readout pattern for a given source brightness that has been generated in a table in JWST. Alright, so here we'll use the bright one. And then you have the option to use the number of groups, number of integration, and number of exposures. So for the ETC, the number of integrations and the number of exposure are completely redundant. But you can imagine the number of exposure as a given detrain pattern. So I won't change the parameters here. And on the bottom, so there is a line providing the total exposure time. So this is the actual photon counting time without any overheads included. So here we see that the observation that I have simulated is very, very short, 21 seconds. The last tab is the strategy. So the strategy is a very important feature. This is how the signal-to-noise ratio will be computed on the simulated images. So basically, it will be done with standard aperture photometry. So here for imaging. So for the aperture, you have two options to put your aperture in the simulated image. So either you center the aperture on the source, or you can specify an offset on the scene, which might be important if you have, say, some extended sources or multiple sources in your scene. And then the other parameter is the radius of the aperture. So we recommend to use a radius of 0.75 or 1 FWHM at that given wavelength. So if you don't know the size of the PSF in that feature for this instrument, again, go to JDocs and look for the given size of the PSF at the given wavelength. So here I know for this feature that I want a radius of 0.07 arcsecond. And then for standard aperture photometry, you have to design a way how you will estimate and subtract the sky background. So in the ETC, you have two options. You have the standard background region, in which the sky will be computed in an annulus surrounding the aperture. So you have to define the inner and the outer radius of the aperture. Or you have the option to use the noiseless sky background. So if you use this option, the sky background won't be calculated from the simulated image, but instead it will use the pre-computed value from the statistical distribution that you have chosen in the background tab. But here I have a very simple scene, so I will use the standard background estimate technique using the default parameter, which are right. Alright, so now all the parameters for my simulation have been generated, has been defined. So I will click on calculate. So the calculation is running. We see that because it's highlighted in blue in the calculation table. Alright, so the calculation is now done. We have a summary of the exposure time, a summary of the SNR on my target, and there is also the status of this calculation, and we see here there is a warning. So we'll go directly the reason of that warning. So in the bottom of the workbook, we have the outputs of the ETC, so the images on the left, so the SNR map, the detector image, and the saturation map. So here we see that some pixels are saturated, which might be the reason of the warning that we have in the calculation table. In the middle, we have the plots, so the estimated aperture flux from the aperture photometry, the background, the SNR as a function of wavelength, so here we have a single photometric point, and the SNR as a function of time. On the right, there is a panel dedicated to the values that have been used and generated by the ETC. So there are several values that might be of interest, especially the number of cosmic rays in a given integration, but also the extracted flux in electron per second in your image. So for NIRCam, this value is important because it will help you to choose which readout mode is in the best in your case. So again, go to JDoc and look for the table once you know the brightness of your source. There's also the option to download all the data products that have been generated by the ETC, so the images and the plots that fit as FIS file, but also the table as an ASCII file. And we have the warning. So the warning here mentioned that there is a partial saturation in my simulation. So the saturation is handled in two ways on the ETC. So there is the full saturation case in which a few pixels are saturated at the first group in our observation. So it means that those pixels cannot be used for any analysis by the ETC. So it's basically a showstopper. for the ETC. The second option is the partial saturation, so it means that the pixels are saturated at the end of the ramp. So most part of the ramp can be used for any analysis. So it's up to you to decide if you're okay by dealing with a partial saturation or if you're not. But here I don't want any saturated pixels, so I will basically reduce the number of groups in my ramp. So I'll say to 5 and click on calculate to update the simulation. Alright, so we see now there is a green check mark in the calculation table, and we don't have any saturation anymore on the pixel. Alright, so that's it for a very simple case, the imaging of a very simple point source. But I will show you more advanced options. So now say you want to do some parameter space exploration, so you have two options. The first one is use the batch expansion. So using the batch expansion, you have the ability to duplicate your simulation for every filter that is available in this instrument. So it means it will generate many rows, especially for NIRCam, with the simulation by varying only the filter in your observation. The other option is to explore the effect of the exposure time by varying the number of group and number of filtration. But because I'm saturated quite easily in this simulation, I will simply play with the number of integration. So the batch expansion will generate many rows in the calculation table, one for any for every parameter combination. Alright, so all the calculations now done, and if I want to compare the result, I basically checked all of them, and go to the bottom panel. In the SNR as a function of time, we now see the improvement of the SNR as a function of the exposure time. Alright, and we have here a summary. We see the increasing exposure time and the corresponding SNR. The other option, if you want to explore different parameters, say the readout mode of the subarrays or the strategy, you can basically select a calculation and copy it and make a new one. And in a new one, say we will use another readout pattern and see whether the SNR has been improved or not. So I will select those two, go to the SNR, and basically we see that here the SNR is higher actually for the bright one readout pattern than the rapid one. Alright, so that's it for the imaging capability of the ETC. So we can use the same source and scene to simulate a spectroscopic observation with James Webb. So we'll use a fixed slit mode on NIRSpec. So I will create a new table, a new row in the calculation table. Alright, so the same parameter on the right panel. So the scene, I will use the same scene. Background, I will use the same level. Instrument setup for spectroscopy. Here you will be able to use the mode, actually the slit. So I want to do some time series observations. I will use the S1600A1 slit, a very big slit actually. And so the combination of the grism and a filter. So I will use this one. So here there is a warning. Wavelength 2.95 micron in the aperture spectral extraction strategy must be in the range of 0.71-0.27 micron. What does it mean? So we'll go to the strategy. So for spectroscopy, in the ETC you have to choose a given wavelength of interest at which all the values will be computed by the ETC. So the default values is actually way too far in the red, and outside actually the wavelength range of the given filter that I chose. So I have to pick up a smaller wavelength, so I will use the 1 micron, which is within that range. So I will center my aperture on the source. I will actually increase the radius of my aperture because I want to do some time series, so I want to use a very large aperture. And for the background, since I have enlarged my aperture, I have to push further away my sky annulus. So alright. And the last one is this detector setup. So for NIRSS, there is a subarray for every slit. I will use this one, which will provide the entire spectrum. Readout pattern, I will keep the default one. Alright, so now I'm done. I click on calculate. So the calculation is now complete. So we see in the output that the trace actually on the detector. We also see the spectrum of the source, actually the signature ratio as a function of wavelength, and we have the same information in the table. So you can do the same batch expansion and the same copy and paste option to explore the parameter space for spectroscopy in the ETC. Alright, so actually that's it for the demo, but I will show you just some more advanced features. So we will go back to the Scene and Source tab. On the bottom right, in the table, actually, we see in green all the calculations that use the scene and the source that we have defined here. So it means that if you make a change of the parameter of your source, it will immediately affect all those calculations. So if you want to explore the effect of a given parameter of your source, we encourage you to actually duplicate that source using the same copy and paste option. Same for the scene, and here give a different name. So here saying you want to see the SNR for a planar target. So basically make those change on a different source and then use those source in a different calculation if you want to play with. So the ETC, with the ETC you can generate very complex astrophysical scene. So as I said, for instance, if you want to simulate a source with multi-component emission, there is a trick. So basically you can generate a source with say, a blackbody emission. You can also create another source with a reflected light component, so using a stellar spectrum. And if you want to make basically an object looking like a comet, for instance, you can basically make a scene and use those two sources, so one with the blackbody emission, one with the stellar spectrum, to mimic a multi-component source. Alright, so that's it for the ETC, and we'll now move on with Loic on the APT.